Okay, so we've done a little bit more on sets to introduce the idea of subsets and power sets. So let's keep pushing along and look at other things that we can do to sets. So some set operations. So union and intersection are probably ideas that are familiar to you, but let's define them slowly and carefully. So let A and B be sets, then the union of A and B, so A, this little U symbol B, is all the elements X that are in A or in B. And indeed, you'll see that there are definitely similarities between how the union behaves and how the disjunction of propositions behaves, disjunction of statements. Continue to intersection. So the intersection of two sets A and B, written here with this upside down U symbol, so just the upside down version of that symbol there. So this is equal to all elements X so that X is in A and B. And again, we see parallels between how the intersection of sets behaves and how the conjunction of logical statements behaves. A little bit more here, that if the intersection of two sets is empty, then we say that A and B are disjoint. So when we talk about disjoint sets, we mean that the intersection has no elements in it. So a few bits of examples and notation here, just to be a little bit careful about your notation. So it's very easy to confuse the notation for sets and statements because they look similar because they do have similarities. That's why we use similar symbols. So please use the union symbol when we're talking about sets and the or symbol here, disjunction symbol, when we're talking about statements. Similarly, intersection and have similar symbols, but please use the right one in the right place. Because though there are parallels between these set operations and logical operations, they're not the same. They act in different spaces on different objects. So, a few examples here. If we take A to be 1, 2, 3, 4, B to be the set of prime numbers, C to be the set 4, 5, 6, 7, then the union of A and C is 1, 2, 3, 4, 5, 6, 7. And of course, even though 4 is in A and C, it doesn't appear twice here because a set only can tell us if an element is in there or not. There's no notion of multiplicity or order there. Now, the intersection of A and B is just the prime numbers that are in A, so just 2 and 3. And the intersection of B and C is just the prime numbers that are in C, so just 5 and 7. So continuing along, we can visualize these things using Venn diagrams. Venn is a mathematician from the 19th century, so this is 19th century mathematics. So the union of A and B, so if this is the set A here and the set B here, then its union is all the elements that sit in both in A or B. So A, things in B, and things that are in both A and B. Similarly, the intersection here, we have the set A and the set B, and the intersection is just the elements that sit in both A and B, so this overlapping region here. So, another operation we can define is the difference between two sets. So if we take sets A and B, then the difference A minus B is the elements in A that are not in B. And again, it can draw a handy picture of this to keep it in mind. So here's the set A, here's the set B, and the difference of A and B is just the elements in A that are definitely not in B. So this region here is not included. And clearly this is not commutative. A minus B is not the same as B minus A in general. So a little bit more notation here, a few more useful terms. So the universal set U is a set from which we draw elements. So typically in many of the applications we're doing, the universal set U will be the set of real numbers. And we have to tell the reader what the universal set is, or it's somehow implicit from context. But so given some universal set U, which is telling us where we're playing with our current bit of mathematics, and a subset of that universal set, then the complement of A is just the elements, so we denote it here with this little bar atop A, is just the elements in this universal set that aren't in A. Or equivalently, we can write that X is in the complement of A if and only if it's not in A. And again, this universal set is the set from which we draw elements in the current context. So for many applications, that's going to be, say, the set of real numbers. In other contexts, it might be, say, the set of functions. We have to make sure the reader knows what we're talking about by context, either implicitly or perhaps we should make it explicit. And so we can draw a picture of this. If we have a universal set U here, so here's everything that we're playing with, and we have some set A, then the complement of A, denoted with this A bar, is everything in U that isn't in the set A. So just a few notes and examples here. Be careful with complement versus complement. One of them is this set operation, and the other one is saying something nice about someone. So please try not to get them confused. The difference of A and B is also, rather than written with a minus sign like this, it's also sometimes written with a slash like that, and is sometimes referred to as the relative complement of B in A. It's a bit of a mouthful, which is why we might just call it the difference. And if we're a bit careful, we can work out that the difference of A and B is A intersection B complement. So it's things that are in A and the intersection of those with things that are not in B. So if we take a universal set to be n, so if we're playing with natural numbers, and we take A, B, and C to be as they were just before, then A minus C is everything in A that's not in C, and that's just this element 4 here that's in both, so it's just 1, 2, 3. A minus B is everything in A that's not a prime, so 1 and 4. And A bar, so things that are not in A in the current universal set, is just all the natural numbers that are bigger than 5. Going a little bit further, so we're just introducing a bunch of ideas that we'll play with as we go. So sets don't care about order. We know that. The set of 1, 2, 3 is the same as the set 3, 2, 1. Okay? But for many applications, we definitely need order. We definitely need pairs of objects, and we need to understand this is always the first thing and that's always the second thing. So we need a definite idea of order, and a good example of this is when we see coordinates, Cartesian coordinates, a classic example of this, where we have the first thing, which is the distance along the x-axis, and the second thing, which is the distance along the y-axis. And we can't just flip them around. The order matters. And so we define an ordered pair of elements to be an ordered list of 2 elements. So the ordered pair of 2 elements A and B is just written as an open bracket A comma B, and satisfies the following points: that A comma B is equal to C comma D only when the first things are the same, so A and C are the same, and when B and D are the same. Okay? So the first things have to agree and the second things have to agree. Additionally, AB is not the same as BA unless A and B happen to be the same object. Okay, so this gives us a notion of order. We have a first thing and a second thing. And we'll need this for a bunch of applications, including functions. You've already seen it in context like Cartesian coordinates. Now, let's be careful with our notation. When we put 1, 3 in braces like this, this denotes a set. It's a set of 2 elements, 1, 3. On the other hand, we put it in round brackets like this. This is an ordered pair of elements. 1 is the first element, 3 is the second element. Now, depending on the context, we may use 1, 3 to denote all real numbers between 1 and 3, excluding those endpoints. Okay, so if we're mucking around with functions and things, we might write this down to note an interval on the real line. It is something that comes up in mathematics quite frequently, that we use or recycle notation. And we have to make sure that the person reading it, ourselves or an actual other person, have to understand what we're talking about, sometimes by context. And if in doubt, we should make sure it's clear. If we start to talk about intervals, we should remind the reader that we're talking about intervals. If we're talking about ordered pairs, we should make sure the reader knows that we're talking about ordered pairs. So in the slide that's coming, we're going to talk about ordered pairs rather than intervals. So the Cartesian product, and again, this comes from the same origin as Cartesian plane. Cartesian product of 2 sets A and B, so A times B, so we write this little cross multiplication sign, is the set of all ordered pairs where the first thing comes from A and the second thing comes from B. So all ordered pairs where the first thing comes from the first set, second thing comes from the second set. And because of that, with a little bit of care, we can work out that if A and B aren't empty, then A times B is not the same as B times A unless A and B are the same. So this Cartesian product, A times B, B times A, those are only the same if one of A and B is 0, or the empty set rather, or A and B happen to be the same set. So be careful, they don't commute in general. So a simple example here, if we have the set ABC and the set 1, 2, then the Cartesian product of A and B is just all ordered pairs where one thing comes from here, so we have 3 choices there, and one thing comes from there, 2 choices. So we end up with 6 elements. So we have A1, A2, B1, B2, C1, C2. Okay. And we'll stop there.